So let me start with a quick introduction. So first of all, good morning, afternoon, or good evening, depending where you are. My name is Stefano Galelli. I'm an associate professor at Cornell, and today I'm your co-host together with David Gold and Gilles Torteman. And it's my great pleasure to introduce you to our fourth webinar. Today, as you will see, our guest speaker is Professor Riccardo Taormina from TU Delft. Now, before introducing Professor Taormina, just a few words about multi-sector dynamics. And actually, even before that, so just very basic housekeeping. So all of you will be muted as a webinar starts. Be considered respectful and collaborative. As mentioned, you're all muted. Please stay muted unless one of us calls you for speaking. And if you have any questions, of course, please use the Q&A. We will primarily bank on that as we carry out the Q&A session towards the end of the webinar. And of course, just be respectful of any question that is being asked. As for multi-sector dynamics, just in case you're not familiar with it, what is multi-sector dynamics? Well, it's a complex research endeavor. It's essentially the study of how complex built natural and socioeconomic systems co-evolve over space and time. And you do have a representation of this on the right-hand side of this slide. And so it's by nature a transdisciplinary research area that tries to advance how we understand coupled human-Earth system and the feedbacks that exist between these different systems. Research in MSD is supported by a large community of practice. So this community of practice represents an effort to accelerate development of needed foundational capabilities, and fundamental pillars of these are open science, as well as growing diverse transdisciplinary workforce. And these webinars are part of that effort. So if you're familiar with multi-sector dynamics, probably I'm repeating things that you're already familiar with, but if you're not and you're curious, you want to learn more about the multi-sector dynamics community of practice, I invite you to visit its website or to join us or to join at least the newsletter, or feel free to reach out to any of us. Now, with this said, it's my great pleasure to start today's webinar. Today's webinar is organized by the working group that focuses specifically on artificial intelligence and on how artificial intelligence can help advance our understanding of multi-sector systems. So the speaker is Professor Riccardo Taormina, who is an associate professor at TU Delft, which he joined in 2019 after a short stint at the Singapore University of Technology and Design as a postdoctoral research fellow. Professor Taormina holds a Bachelor of Science and a Master of Science in Environmental Engineering from Politecnico di Milano, and a PhD in Civil Engineering from the Hong Kong Polytechnic University. His work spans across several domains, primarily looks at the intersection between data, computational modeling, and machine learning and AI to address water management problems, especially in urban context. And again, it's my pleasure to introduce him. I'm looking forward to his webinar. So, Riccardo, stage is yours.
Hey, thanks, Stefano. Just one little thing, like I'm from Politecnico di Torino.
Oh, my bad. Yes.
Yeah,
I'm
it's
sorry.
okay.
Yes.
It's okay. You're biased. Okay, guys.
I'm biased.
Yeah.
Go ahead.
I'm gonna share my screen. I hope you can see it. Any problem? Can you see the screen? Okay. Thanks a lot for the introduction, Stefano. It's a pleasure for me to give this talk. As you can see, it's going to be about graph neural networks for modeling water distribution systems and beyond. Because I think especially for this community of MSD, what's interesting is that these techniques I'm going to present are quite flexible, so they can use for multiple infrastructure or multiple type of problems. Okay, we don't have much time, and I have quite a few slides, so I'm going to start. And again, David, if I go too long, just remind me. Right, so this is a bit of an outline of what I'm going to present. So indeed, I would like to first focus on a bit of an introduction so that everybody's familiar with the basic of these techniques. So this is probably my main purpose. And then after that, I want to show you how these graph neural networks, so these AI models that work on graph structures, are actually very useful to work in many domains in the water sectors, but also beyond. Okay, so background indeed. So why are we interested in graphs? Because they're ubiquitous in nature, in also society, and they're very flexible data structure that we can use to model and represent very different systems, you know, from social networks all the way to transport networks. So now I'm focusing on the water sector, which is indeed where I actually I am doing research. And water distribution systems, so are certainly, you know, can be modeled as graphs. The same goes for urban drainage systems. So we're talking about stormwater sewers as well as sanitary sewers. And even if you think about problems that we solve in the field using computational meshes, we can always compute a graph from a computational mesh. So indeed, this is also like something that we can refer to as a graph. For some of you that are interested in river and river networks, indeed, this is another thing that we can model as a graph. So there is many ways in which we can use graphs to model problems in water management. And as for multi-sector dynamics, you know, the logo itself shows you that there is a graph. So, you know, you can imagine that indeed is very suitable also for the broader sector that you know, we are looking at. Okay, so it's very, you know, a good practice to start with some basic definitions. So what is a graph? You may be familiar with this definition that I put there. From a mathematical point of view, usually we can define a graph as a tuple in which we have this set of nodes or vertices which are connected by edges. And there might be some weights connected and assigned to these edges that sort of represent, you know, how important is a connection between two nodes. Another important concept is that of a neighborhood. So basically that identifies, you know, nodes that are directly or, you know, indirectly connected to a specific node that we are considering. Now, we are talking about machine learning on graphs, right? So this is a bit beyond graph theory. So graph theory doesn't really look at the data that is specified on the graph itself, which is actually what is of most interest in this presentation of mine. So what I mean is that, you know, in a graph, we usually can have variables, which can be either static or dynamic, and they're assigned to either the nodes or the edges of this graph, sometimes to the graph itself. So, you know, if you're talking about water distribution systems, so you can think, for instance, as a static variable, the elevation of a specific node, right? And the pressure of the water at a specific node is an example of a dynamic variable. And the same, of course, can go for, you know, the edges, right? Talking about diameters of a pipe or the flow that flows within this pipe. Another very important concept is that, you know, it's difficult to represent a graph, you know, mathematically, unless you basically resort to a matrix format, which is really widely used in the field. And you may be very familiar with the most, let's say, common way to represent a graph in a matrix format, which is the adjacency matrix, right? So it's this matrix that you see on the right of zeros and one, where one identifies whether two nodes are connected or not. So this is a square matrix, as you can see. This is only one of them, it's just the most famous. You know, a very important one in the field of water distribution system, for instance, is the incidence matrix, which basically represents node-to-edge relationships. Something that is very used in graph theory is the degree matrix that basically shows how well connected, let's say, a specific node is by counting basically the number of incident edges to a specific node. I guess that's also quite a famous matrix. Something that I will mention a couple of times during this presentation is something that we can actually derive from the degree matrix and the adjacency matrix or the incidence matrix, and it is the Laplacian matrix, okay? So this is a very important matrix in graph signal processing, and basically it captures both the node connectivity via the adjacency matrix and the nodal degrees via the degree matrix, in a sense. So I don't want to go too much into depth though, but it's very important to understand that, you know, from a mathematical point of view, which then, you know, is how we make these computations on a graph, as we will see. we usually use these matrix representations, and different matrices can represent different aspects of a graph. Okay, now let's move to the actual problem that we are dealing with, which is indeed, machine learning on a graph. Okay, so imagine that you have a problem in which we have a signal, in this case on the node, such as the pressure in a water distribution system. And what we want to do, we want to use machine learning, for instance, to interpolate between the sensors that we have to infer the state of the system in its entirety, right? So this is a graph machine learning problem. And let's say, therefore, we want to use a machine learning model. And if we use traditional approaches such as random forest or feed-forward neural networks, such as a multi-layer perceptron, what we end up doing first is that, okay, we have this very nice structure, which is a graph. And on top of this graph, we have the signals. Well, we completely remove the structure. We flatten everything into this sort of like Excel or CSV, if you will, format, which is what usually is needed in order for us to feed this information to a random forest algorithm or to a multi-layer perceptron. So this is a traditional approach which is lossy, because we're basically removing a lot of information that is actually important, if not fundamental. And the idea, therefore, is to, can we develop machine learning models that digest the graph in its original format, right? So it retains all the very important information that we have, such as, for instance, the connectivity between different nodes, because that's essential for then us to kind of like perform the machine learning task in a good way. Okay, so how do we build machine learning models that exploit the structural information in the graph? Now I'm going to focus a little bit on this idea of structure, because it's very important in general for machine learning. And let's do this by looking, for instance, at a much more, let's say, traditional, let's say, deep learning, at least computer vision example. So imagine you would like to classify this image, right? You want to assign this image to the painter that created it. In this case, it's Van Gogh, right? So you're looking at an image, and even if it is a small image, so let's say we have 128 times 128 pixels, and then we have 3 channels, RGB. So this data structure, this image, is actually, its original format is in 3D, right? It is a 3D format. Now, imagine that we want to classify this image using a machine learning classifier. Again, think about your random forest. Think about a multi-layer perceptron. In order for us to do this, we have to first flatten out all this information. So what we literally do, we transform this cube, if you will, not cube, like a 3D structure, into a one-dimensional array, in this case of almost 50,000, a bit more than 50,000 entries, right? So 128 times 128 times 3, okay? So first of all, we do this flattening. So we completely change the nature of our data. Then we can feed it to our multi-layer perceptron. But what happens now, since we're operating on this sort of like a flattened version of our original data point, you can quickly see how we end up falling into the curse of dimensionality. Because even in a, let's say, conservative situation in which we only have one hidden layer of a feed-forward neural network with 1 neuron for each input, in a sense, we end up having models with 2.5 billion parameters, okay? So this is more or less the size of a small version of ChatGPT. So it makes no sense, right? There must be a better way to do this, right? And indeed there is. And we can do this by exploiting the data structure itself rather than doing this flattening operation. So we move away, in the case of computer vision, from the use of dense layers, which are usually employed in a feed-forward neural network, right? In which, we try to learn weights, the fine connection between pixels, which are really far away from each other. So there is no really meaningful information to capture there. And instead, we realize that, usually we have nearby pixels that are related, and together they create some features of interest, and then we can exploit to solve the task, whether it is classification, regression, segmentation, anything that you want to do in computer vision in this case. And that's why we end up, using convolutional neural networks, right? So we end up building convolutional layers, which have really been transformational when it comes to computer vision and deep learning. Instead of learning weights, we now learn filters, which are structured, and are basically recognizing specific features in our image. So you can think, for instance, of having dedicated filters that basically learn how a star, in this case, is painted by Van Gogh, or, you know, how the tree is painted, how the, you know, like the houses are painted, and so on and so forth, right? So we have this much more, let's say, structured approach, right? And it's also nice to see that once we start moving away from weights and learning filters, so learning these feature recognizers, and we end up basically using even more the data that we have, because some of these features of interest, as I show you here, basically repeat within the same image. And what I'm actually most interested in is the fact that once we learn this sort of feature recognizer, then we can actually transfer much better to a new data point, to a new case study. So in this case, I'm showing how, you know, if you learn how to, you know, how Van Gogh, in this case, paints a star in one painting, in this case, one version of the Starry Night, then you have much higher chances of recognizing the same features elsewhere in a data point that you didn't use, in this case, another version of the Starry Night, which, let's say, was not in our training data set. Okay, so this idea of leveraging the structure is part of a broader concept that we have in machine learning, especially in deep learning, which is the idea of using inductive biases, which are whatever assumptions, let's say, we build into our models, okay? And indeed, by leveraging the structure in the data, we are introducing one of such inductive biases, as we will see. And what inductive biases do, basically, they facilitate learning by guiding the identification of specific patterns in the data that we find interesting, okay? And in this way, as I showed you briefly before, you have higher chances of generalizing better when you are basically transferring the knowledge to unseen data. So in the case of a dense layer, they have no assumptions, which makes them very, very flexible. And that's why we say that a multi-layer perceptron is a universal approximator. It can literally do anything, but it requires a huge amount of data to do so, and maybe many of such neurons. If we move to convolutional layers, in the case, let's say, of computer vision, we say that locality matters. So we build the models, these convolutional layers, in a way that we focus on these local features. So we are not as flexible, but we are much more data efficient. And for computer vision, we usually end up doing a much better job. All right. Now, convolutions are really powerful, although it's a very simple operation, as you can see, of basic, point-wise multiplication and addition, right? So convolutions, if you're familiar with it, I don't want to go too much in depth, but basically they end up implementing what we call a spatial inductive bias by learning these filters that are able to extract features locally from the input that we see, in this case, images, okay? Now, images are regular grids, so they're kind of easy to deal with. Now, once we move to a graph, now we have a big problem, because, it's not that the number of neighbors are fixed, as in the case of, learning filters, in a basic convolution. The number of neighbors changes from node to node, and also there is no natural orientation or ordering of the neighbors. There is no like up, bottom, left, and right, okay? So these things make things very, very complex. Now, luckily, there is a way in which we can generalize convolutions from a regular grid to an irregular structure such as a graph. And this operation comes from graph signal processing and is known as graph shifting. It is not rocket science. We will see there is a very basic operation as well. Basically, you need to pre-multiply the node signal by something which is called a graph shift operator, usually identified with the letter S. May sound daunting, but actually any square matrix that somehow reflects the structure of the graph can be used as a graph shift operator, okay? So when I mentioned at the beginning, the adjacency matrix, the Laplacian matrix, well, those are graph shift operators, okay? So a generalization of the very powerful linear operation of convolutions on regular grids is done on a graph by using this graph shift, which is essentially, just aggregation or propagation of signals by a linear combination of the values, in the neighborhood, okay? So it's really nothing very difficult to do. It's easily visualized, for instance, for the case of using an adjacency matrix as the graph shift operator. So in this case, if you want to do the graph shift in the convolution for node 5, basically, using the adjacency matrix is basically the sum of the signal at its neighbors. Okay, so it's kind of intuitive, I hope. And then you can make it as complex as you want. For instance, you can add a self loop if you think that also the information on the node itself is important, and you end up having something like this. In general, what we usually do, we use this Laplacian matrix that I briefly mentioned before, because basically it facilitates stable signal propagation by balancing the importance of node connectivity with also the degree of each specific node. Okay. Now, this may be a lot to unpack, but in the end is, again, a basic operation that generalizes convolutions on a graph. And we saw that convolutions are very powerful. They are powerful, but they are still linear operations, right? So it is limited. So like we do when we build convolutional neural network, after the convolution itself, we can learn the filter's weights, and also we add nonlinearities to improve the complexity of our representations. So we do the same basically with graph neural networks. So what we do, we add some learnable weights, and then we add some nonlinearity. So we move from graph convolutions to graph convolutional layers, okay? And if you look at the mathematical format for this specific layer, like a genetic layer, it's not really that complex. It's very similar to other basic deep learning layers. So as you can see, let me see if I can maybe have a pointer here. No, not this one, pointer option, laser point. So this is, let's say, the hidden representation at layer L, which is computed by applying this nonlinearity, such as a ReLU, on this argument, which is basically x here is the value of the hidden representation in the previous layer. And this theta here is the weight parameters that we learn. And this S here is this graph shift operator, so this Laplacian that I mentioned before, okay? So it's not really like rocket science. It is very common to other things that we do in deep learning. And we end up building this graph neural networks in this way, the simplest of which are the one that I just described, which are known as graph convolutional neural network, okay? But we can resort to more complex architecture, so we can use graph attention. So attention is what made transformers and ChatGPT so popular. We can do the same on a graph. And we can even go to a much more generic representation, which is known as message passing. Again, we can do a lot of things with this graph neural networks, but I'm going to focus mainly on this stuff today. Okay, last slide, I hope, for the background section, which is already quite long, but as you can see, there was a lot to unpack. Like we do with other deep learning models, going in depth with graph neural networks basically allows us to reach larger and larger neighborhood, okay? So if you want to span an entire graph, then what we usually do, we stack more layers on top of each other, okay? So you can see that basically, at the beginning, we only consider, let's say, the immediate neighbors to compute the representation in a specific node. As we go deeper in the network, then we start basically summoning up, information coming from the entire graph, okay? So depth is sort of like proportional to width, if you will. Right, now, let's move to the application, and I will start from water distribution system. So we'll spend most time on it to illustrate some results, and then I will quickly move, hopefully, towards the end to some other problems. So this is the work of Bulat Kerimov, mainly, a PhD, now a PhD because he graduated like a month ago, and that I had the honor and the pleasure to supervise in collaboration with NTNU in Norway. We actually got his PhD. So the main reason why we started this project was to look into this idea of transferability that I quickly illustrated before. Okay, I will try to show you why. So again, is this idea that we learn something on the training data set that then generalize quite well to unseen case studies. Okay, now let's consider water distribution system. So what we wanted to do was to basically build a model that could digest data coming from multiple of this water distribution system, and then being able to make prediction somewhere else, unseen, as long as it was another water distribution system. Why would we want to do that? Well, because the problems that we have in the water sector, like in many other sectors, are really global. And one big problem is that of non-revenue water, which is the water that we lose, due to leaks or burst in the network, or sometimes theft, right? So it's a global problem, right? So it makes sense to tackle it with a global model, like we do, for instance, in other fields, such as weather prediction with AI these days, or even rainfall runoff modeling with AI and so on, right? So this was the idea. And why? Because, you move to situations such as this, like in Singapore, where you have a fantastic physical infrastructure, which is also supported by an amazing digital infrastructure. So you end up having like a lot of data and relatively few problems to solve. But when you talk about this problem of non-revenue water, in most of the locations, most of the water utilities actually need a solution. They have a huge amount of these problems, in this case, anomalies, right, in the system, and very, very few sensors to use, right? So can we use a model that has been trained on, let's say, high resource settings and transfer them to low resource settings, right? So this was the motivation. So this idea of transferability is very, very important. Now, unfortunately, in the water sector, we know that we don't have much data. Water distribution systems are safety critical infrastructure. So to begin this exploration, we had to sort of like use simulations, okay? So we end up looking into surrogate modeling, which is something that is very widely used in MSD research as well as a whole. And basically here, the scope is to, substitute accurate but computationally expensive numerical simulators with machine learning counterparts, usually by training them on some simulations and then being able to generalize, right? Now, we basically trade accuracy for speed, that in this way we can allow time-sensitive applications such as, uncertainty estimation, real-time response, and so on and so forth, right? Now, even though the scope is not as appealing as the one that I initially described, right, having a global model that can predict leaks everywhere, still there is a purpose in developing, let's say, GNN-based transferable surrogate models for water distribution system, because usually the actual state of the art is not always data efficient, and also these models usually do not generalize, okay? So you train them specifically for a single case study, which is kind of like defeating the purpose sometimes, because you need to run a lot of simulations to then build this model in the first place. Now, how are steady state, we talk about simulations for water distribution system. Usually we talk about steady state simulations, okay? So the time component is not important. So we usually use steady state. And we employ hydraulic solvers such as EPANET or Winter, for those of you that know. They take into account the topology of the water distribution system and enforce math and energy conservation, okay, to basically give us pressures in all nodes and flows in all pipes, okay? So this is the usual problem that we solve when we talk about simulations of water distribution system. And we have a lot of inputs, as you can see. The main forcing are the water demand, so how much water is asked by the customers, and also, the energy that we have in the reservoir, meaning like, the gravitational energy of the reservoir from which the water comes from, or it can be a tank, or we can have pumps, of course, providing extra energy. And we have very important pipe parameters, such as, the friction coefficient in the end of the pipe, because that determines the amount of energy that we lose in the network, okay? Okay, I hope you're familiar a bit with this. Again, the core is this idea of mass and energy conservation, which basically means that at any given junction in the network, the amount of water that comes in is equal to the amount of water that goes out, including the water demand or the water coming in from a tank, for instance. When it comes to, so this is continuity equation, essentially. Energy conservation, it means that between two nodes connected by a pipe, they have the same energy, but the head loss, the energy that you lose because of friction mainly, for the water to move from A to B, okay? And we usually end up having like a nonlinear system of equation that we have to solve, in an iterative fashion, losing quite a bit of time, even though the algorithms that we have are quite efficient. Okay, now finally some GNN. So the first work that we did was this first exploration, trying to see whether we can build a transferable model with this graph neural network, and also see whether graph neural network can improve, performance against, let's say, multi-layer perceptrons, which are usually employed in this case. Okay, so this is a typical graph neural network architecture, which is usually employed for many problems related to physics that you want to do using AI, okay? It's an encoder, processor, decoder sort of architecture, where the encoder basically maps the input feature that I showed you before to a higher dimensionality, right? To have some better representation. Then we can process with the actual engine, which is called the processor. And here is where the GNN layers basically start doing their computation. Basically, they propagate and aggregate this information, coming from the input to then, give a final hidden representation that is decoded by another neural network, an MLP, so multi-layer perceptron, and give us the outputs, okay? So it's a kind of a complicated process, but it's usually done in this way, all right? And if you look at the processor itself, it is a series of these graph neural network, convolutional neural network layers that I described before. So basically, they look more or less like this, okay? So this is the hidden representation, which basically is a nonlinear function of the previous hidden representation with some weights and the graph Laplacian that I described before, okay? Now, the first experiment wanted to see on individual case studies that you can see here depicted, how good these GNNs are compared to multi-layer perceptrons, okay? So that's the first thing that we wanted to do. There were already some papers, showing that you can use GNNs for specific individual case studies, but there was never made like a comparison against, let's say, a more basic approach. And basically this with their 6 network of variety, like number of pipes, so bigger, smaller, and so on. And we basically had 10,000 samples for each of these networks. Then we do some randomization of the input features, such as the demands, the diameters, the roughness coefficient to create a bit of variety and complexity. And then we try to check, different GNNs and different MLPs, so multi-layer perceptron that we use for comparison, okay? The results showed us that actually the GNN didn't work that well. So the performance were actually similar to those of the multi-layer perceptron, much better only in a few case studies, but usually more or less at par. And since we are aggregating this information on the entire graph, right, this is like a recurrent operation. So it makes this model actually much slower than the MLP. So similar performance, but slower. Not a great thing. And if you look at the test data set and you look at the graph between the simulated pressure, which are used as ground truth, and what we predict with our models, then you see that for both cases, actually, it's not the ideal scenarios, right? It's not really pretty what we're looking at. Okay, this was one thing. The main thing was trying to see whether actually there is potential to learn a single model for all the networks, okay? And this is something that we end up doing. And indeed, we showed that it was feasible, although the results, again, were not that good. So, we sort of like, it was like an initial sort of like insight. Okay, we can do this, but it is not really working well. And then we started looking into why this didn't work. And the main thing is that, two main things. One thing, as I mentioned before, stacking layers means that we're going farther away in the network, right? At most, we could span 18 nodes away. So from each node, we can consider up to 18 nodes away when it came to the computation of these outputs. But then if you kind of compare this width of 18 against the actual graph diameter of the network, and by graph diameter, we mean the longest, shortest path between any two nodes in the network, we start seeing that actually we fall short for most of this network, okay? So maybe the network was not big enough. But the biggest problem is something that is really inherent, like intrinsic with this type of GNNs. So basically, it's an issue known as oversmoothing, which is actually quite important to keep in mind. And it's the main limitation of traditional graph convolutional neural network, okay? So that the way that this propagation and aggregations are done using this Laplacian that I showed you before, basically are done in a way that it favors like a smooth transition, okay, between, you know, the signal between across adjacent nodes, okay? So anytime that you add such a layer, basically you end up introducing a new multiplication for this Laplacian, more or less. But this is what this ends up doing if you do it many, many times. So basically, you know, you keep propagating this signal by trying to reduce at the same time the differences that you have across nodes. And unfortunately, smoothness ends up basically, you know, making all the nodes having similar embeddings, which in the end translate to all the nodes have more or less the same pressure, which means that you have basically no flow, more or less. Okay, so you're really not, you know, doing yourself a favor. Okay, so this type of GNN is very good at capturing the structure of the network because it operates on a graph, but it introduced this problem of over smoothing, then limits the expressivity of this GNN itself. Okay, so we need to do better than this. And luckily, we did this in a second paper, again, of Bulat, where basically we moved away from a node-based representation to an edge-based representation. Okay, I'll try to explain what we did simply if I can, given that I still have only 15 minutes left and I wanted to talk about other stuff. So basically, you know, you can either focus on the nodes, which is the traditional approach, or you can focus on the signal on the edges. When you focus on the nodes, basically you actually predict pressures, and then from the pressures, you derive the flows, okay? You can do the other way around. You can start predicting the flows, and then from the flows, you retrieve the pressures, okay? Now, what in the end, these models look very similar, okay? But instead of working on, you know, let's say instead of these hidden representations and these original signals being specified on the nodes, you end up having them on the edges. And instead of using, let's say, the Laplacian that I showed you before, we use another Laplacian, which is called the edge Laplacian, okay, which actually operates on the signal on the edge. And it seems like a very kind of like, you know, minor change, but actually the change that it has on the actual processing of the data is very big. You can see here the differences when we move away from a node Laplacian and a node representation of the system to an edge representation of the system. So as I mentioned before, this multiplication by a node Laplacian end up promoting smoothness, okay, for the signals on the nodes, and this leads to over-smoothing. If you move to the edge representation, instead of like enforcing smoothness, you actually enforce mass conservation, which is a good thing, because basically now we are adding another inductive bias. So not only looking at the structure of the data, but also adding the physics. For those of you who've been working with physics in neural networks or this hybrid model, it's something similar to that approach, okay, to pins. But in pins, you specify this on the loss of your deep learning model. In this case, actually, we are basically doing this in the convolutions, okay? So we add this extra inductive bias of physics, which we think is a very good thing to do. And it comes like for free if you move to this edge representation. Now, you need to do a few things in order for you to move to this edge-based representation. I invite you to read the paper to have more information about it. But the most basic thing that we end up doing, that we need to do actually, is to then specify also the water demands, which, as you can see, are featured here in the mass conservation. So water demands are a nodal feature. We need to specify them on an edge. So what we need to do, basically, we have these virtual links in which basically the demand then becomes the flow that we enforce in those virtual links, okay? So by doing this, we can work with this dual graph, which basically has the edges as the nodes and vice versa. And we can do this kind of convolution and then end up sort of like enforcing a mass conservation, okay? Now, once we start doing this, we start seeing, you know, I will just go a little bit faster here, much better results, you know, both in terms of head and flow representation. So we are comparing here against the state-of-the-art GNN on the nodes, and you can see the performance are actually much better, especially when we start to add more variability into our training data set to make things a little bit more complex, okay? So we start seeing these very interesting improvements. As you can see here, the performance are actually quite good, sorry, on the test data set. There's a very good match between both nodal and link feature, nodal pressure and flows on the links. And also, one thing that you want to do when it comes to meta modeling or surrogate modeling, you also want to see some speedups. And you get good speedups, very good for small networks, and still like decent for larger networks, without doing any crazy, let's say, machine learning engineering to improve the code for performance. But the most interesting thing, again, is this idea of transferability. So can we transfer better now? So we use this edge-based neural network, and we trained them on 6 case studies that you can see here on the left. And then we tested them completely out of domain, meaning completely with networks that we never seen before. And what you end up seeing in the end is that the performance are actually quite good. So we start having, R square of, more or less 0.9 and above. And it's actually very, very nice. Now, again, this is a very good improvement because we end up like having this very good transferability, which was the original thing that we wanted to do to start with. Now, I don't have time to show you the third paper of Bulat, but what's very important for you to know is that we saw that by introducing mass conservation, we actually have much better performance, and we basically can transfer much better. If you also introduce energy conservation, which is the other, let's say, basic physics principle that we use for solving water distribution systems using numerical models, then basically you don't need even to learn anymore. You don't need machine learning anymore. You can implement an algorithm that is still basically exploiting the fast computation of GPUs, okay? But at the same time, can converge to the exact steady state solution that basically the simulation gives you. And we can also have very good speed ups of 10,000, for small network, and I think still 100 times faster for smaller networks, okay? There are some limitations, but please read the paper if you're interested in this, okay? Now, I have very little time, I know, David, but I will try to quickly tell you then how this type of GNNs work very well also for other type of infrastructure. So first thing we're looking at, again, surrogate modeling, but for stormwater systems. And this is work done by another PhD that I have the pleasure to supervise. And this is Alexander Garzón-Díaz at TU Delft. So this is the main core of his thesis work. So here we're not looking anymore into steady state. Here is a dynamic problem, okay? So the method modeling that we do here, basically, let me show you like this. We start from, the topology, which is, again, this urban drainage system or the stormwater system. And we have runoff as input, not water demands. And we have some initial conditions, say the amount of water that was in the system before. Now what we want to do is to predict the hydraulic head in all the nodes and the flows also in all the pipes of the urban drainage system. But this time we have to do it recursively, okay? Because it's a dynamic problem, right? So we make prediction and then we feedback this prediction to make new prediction until we have the entire simulation, okay? So even in this case, we show that actually we can train, improve on top of, let's say, traditional models. You can see here some result in terms of NSC. And then we can transfer to parts of the network there was no use for training our models, okay? So this transferability thing holds. And we have, of course, sometimes not great prediction, but most times we have pretty good prediction, even if you've never seen this part of the networks in our training data set. Okay, we can do the same for flows, as you can see here. And unfortunately, the speed up is much lower. You can see here is only 7 times for this kind of like realistic network, which is actually part of Utrecht. David, is close to where you work. So luckily, though, in recent development that we are publishing soon enough, we hope, we managed to sort of like move from this one step ahead thing to a multi-step ahead thing. And then you can see that the speedups are really, really much bigger. We're talking about tens of thousands of times, okay? And you can find a very good trade-off between speed and accuracy. And lastly, what I want to show, which is also very insightful because it's connected with the reality of the problems that we start to solve, we see how important it is to add more layers to our neural networks. Basically, since, it's a real problem, right? So, if you have water somewhere, in the network, a minute from now, this water will travel to another point in the network, right? So, based on the time step of the simulation, in this case, you will have different junctions that end up being connecting to each other, right? And we see that, if you want to make a prediction by using only one layer, so just looking at what happened in the node before, let's say, then we have this flat line, so we don't learn anything. So we need, in this case, to at least have 11 layers in the network, so connect, junction which are 11 hops away to start having very good results. Okay, so this is something interesting that we are publishing now. Okay, in very few minutes, I see there are, still, okay, it's already 47. Yeah, I am 40 minutes here, but okay, I'll try to make very, very briefly. They work, these graph neural networks, also very well for, predicting floods in a spatiotemporal fashion on a 2D map. So, okay, motivation, you can understand why we need to model floods. Well, we usually use numerical models which are basically solving the shallow water equations using methods such as finite volume methods, but they can be very slow. Okay, so we need to accelerate them. And again, so what Roberto Bentivoglio did, so which is this other PhD that I have the pleasure to supervise, who is doing this work, basically he developed a graph neural network that kind of mimics the way that the finite volume method that you might be familiar with works to solve the shallow water equations, okay? And as I mentioned before, from a mesh, because this problem is solved on a mesh, you can always end up having a dual graph, right? And therefore we can use GNNs. So we have, again, a very similar GNN to the one that you saw before, but now we are working on a mesh, right? So we have basically our inputs are DEM, sorry, oops, I went too fast. Our inputs are DEM information, and then we want to predict the flows and the water level in all the cells that we have in the domain, okay? One other thing that we did in order to achieve speed and also kind of like cover much larger case studies, we ended up developing like a multi-scale neural network, okay, that works at different coarser level of the mesh. Don't have time to go too much into details on that, unfortunately. But anyway, what we see, this is a case for a dike bridge floods that is occurring here. We see that indeed, this model predicts very well. So you can see this is the output of the AI model. And on the left, you see actually the ground truth, which is represented by this high fidelity numerical simulation. Okay, so this is very interesting. This is a synthetic case study, but we do very well also on realistic case studies. So this is a dike ring in the Netherlands between Utrecht and Rotterdam, as you can see. So even for this case study, we have very high accuracy once we compare our system against the actual simulation. Okay, the very last thing with this is the last slide, luckily, that I have. So with this multi-scale neural networks, graph neural networks, now we can also cover much larger case studies. So the one that you see here, I hope you saw before, and basically it's up to 250,000 cells, which is kind of big, and we achieve speed ups of 30,000 times compared to the numerical simulator, and with pretty high accuracy. So if you are EGU, next week on Monday, I think around lunchtime, Roberto is going to present this, so please attend this presentation. And it was very long and too many things, maybe, sorry for that, guys, but that's all I have. So if you have any question, please ask.
All right, thanks very much, Ricardo. Yeah, it was really nice. I learned a lot from this presentation, so thank you. If folks have questions, I think feel free to raise your hand and then I'll call on you, or if you're more comfortable, put it in the chat and I can read off from there. So I'll give it a second, otherwise I can jump in with a question. Yeah, Jillian, we can start with you.
Hi, Ricardo. That was awesome. Thank you so much for the background. I needed that, so I appreciate it. I was curious, with the first work that you were talking about with the nodes and the edges, it looked very much like a map and it looked very much like points and lines. was that data spatially explicit, or were you just showing the node in a way that flowed easily?
Yeah, no, that basically thanks for the nice work, by the way, and that was just you know, like it's a computational model of a real system. So those points have coordinates and they're actually connected like that. There are some simplifications, but that's actually, you know, how the networks on which these models were based upon were actually truly connected. So yeah, so that's indeed, those could be points on a map. So, you know, if you look at the computational models of what we use, they have coordinates that are meaningless because you have to refer them back to the original system. I don't know if that answered your question.
Yes, it did, because I specifically work, like you had mentioned earlier, where it was kind of putting the rasters on top of one another and then bringing it into a single array of CSV file. That's what I do all the time.
Yes.
And so being able to learn about a new way and a new way of thinking about this has definitely started getting my gears going. So thank you, I appreciate it.
Absolutely. Yeah, they're very good for modeling spatiotemporal stuff, let's say, in something that it's not really looking like a grid, but more like a graph. So, you know, transport networks, any type of networks, social networks, if you will, you know, so I think they're very versatile for many problems that we have in our field.
Awesome. Thank you.
Well, and I guess I can jump in with a question kind of building on that last comment. Ricardo, this was a really nice overview of water distribution systems, and then thinking also about shallow water and flooding. Where do you, in your opinion, see the most opportunity for GNNs in this type of methodology in MSD science more broadly? You know, you mentioned transportation or other applications, but is there anything that you think is particularly advantageous for this type of methodology?
Yeah, no, a very good question. Thanks. So I can tell you already that I think when it comes to AI-based modeling, water distribution system, and other networking system, these are sort of considered state-of-the-art in a sense, but with all the limitations that you have from learning from simulation. So in transportation, they've been around for longer. Also, power grids have been around for longer, and they are indeed more, you know, more often than not cited as state-of-the-art machine learning system. Okay. So they are really promising for ideally any type of you know, of networked system, and also you can work on multi-graphs, meaning that you can work on, you know, interconnection between different graphs, right? So you can think about interconnected infrastructure and whatnot. Usually, the transformer-based methods, which are those that also you use in large language models, they could be even more powerful, but they're usually you know, because they are more flexible, they can learn, you know, independently, let's say, of the graph that you're feeding them, but you can still condition them on the graph that you want them to kind of work on. But they need more data. But they are faster because, you know, they don't have this recursive sort of like approach that I mentioned. They can do this thing usually in a more, you know, more fast, you know. But they require, you know, more data for sure. And sometimes they're difficult to implement because, you know, they start looking into connection among every node, and this can spam in memory. I would say that, you know, they are ideal candidates for a lot of problems that we have in our field. The thing is, you need the data. So kind of like tired of working with the simulations, because in the end, you know, like the simulators that we have are really good. What the simulators are not good at is kind of like making the most of the actual data that we would like to feed them. So if you have a simulator, you need to calibrate it, right? So the calibration basically is an indirect way of fitting your model and its predictions to reality, right? If you have a machine learning method, like a deep learning method, that can also introduce the physics a little bit of what we've seen today, for instance, then you have this possibility of using the data in a much more natural way to actually, you know, because basically you can use a gradient descent and you can do this much more seamless integration. And if you link, for instance, to you know, differential hydrology, right? That's also something that you get, like the possibility of more seamlessly integrate this external information. And that's what I see the biggest advantage of AI against simulators, okay? Sometimes you can use simulators, but if you want to model the physics, of this type of processes, the better advantage that you may have. And this is under researched though. It's not like something that has been. So that's what I would like to focus more in the future.
Excellent. Thank you. Yeah, that's exciting. Jill, do you have another question?
If anyone else has a question, you're welcome to jump ahead of me. But I do have one more question for you, Ricardo. So regarding your paper in which you use the edge-based representation as opposed to the node-based representation, you had said that you had found like a lot better results. And do you think that that's because it like kind of goes back to what you were saying earlier, where it takes advantage of the like inherent structure, like kind of from the to the from, showing where it's going? Can you kind of talk more about that and why it was so much more impactful than the node-based representation?
Yeah, no, absolutely. Actually, the structure was not the thing there, because both node-based and edge-based, they do capture the structure, okay? It's just like they look at two different ways of looking at the same graph in a sense, okay? So it was not so much the structure. And when you're working with this basic GNN based on graph convolutions, the main problem is that if you focus on the nodes, then basically you end up suffering this over-smoothing thing, which is kind of difficult to get rid of. You can use more complex version of these GNNs, like the one that use attention or use like residual connection, to get better result on that side. Okay, you could do that. But what we found more interesting is that if you move to the edge-based representation on top of the what I call inductive bias of putting the structure into the model, you also put this powerful inductive bias of mass conservation, which is at the base of how this water distribution system works, at least in steady state, condition, abstraction. So you actually kind of like do yourself a favor. And what was leading to over-smoothing, so this multiplication for the Laplacian done many, many times, actually helps you enforce mass conservation, because moving from the node Laplacian to the edge Laplacian, you basically, instead of like looking into smoothing the signal on the nodes, you enforce conservation of the edge signal. So it's really this extra kind of boost that this physics-based inductive bias gives you. So when you add inductive biases, you let these assumptions do most of the work for you. So you can learn more from the data on one hand. And on the second hand, you learn more general representation. There is nothing more general than physics, right? If you will. And that's why you end up having also better transferability. But there are different ways to do this. Other people, researchers in Bielefeld have done it, a researcher at UT Austin have done it in a different way, a researcher in Italy also looking to something similar. So it's different ways of trying to use whatever you know to facilitate the work from the machine learning model. So that it learns more from the data that it has, okay? So it's, okay, I know this, so I'm gonna use the data just to really understand the things that is not really that well explained. But focus more on the more interesting stuff.
Okay, awesome. Thank you.
Thanks for
excellent. Well, we're right at the hour, so I think we can wrap. So thanks again, Ricardo, for the excellent presentation, and thanks everyone for coming to this MSD webinar. This will be posted on the MSD YouTube channel, so if you want to take a look back at anything that Ricardo said, you can find it there in the next few days, and also keep an eye out in the MSD newsletter and social media. We have several more MSD webinars for AI in the MSD working group scheduled, so we'll be announcing those shortly. So thanks again, everyone, and have a good day or evening, depending on your location.
Thanks, everyone. Thank you so much. Bye-bye.
Thanks, Ricardo.